Is keeping the Voyagers active a waste of money and time on the deep space network? Could you play catch with a baseball mass black hole? How confident are we in the distance ladder? And in our Q&A plus version, does it make sense to film a movie in space? Answering all that and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Bentation Funkiloglio. If a primordial black hole was light enough, could one play catch with it, assuming that you could see a subatomically sized black hole? Sure. I mean, a primordial black hole can be any mass. So it could be the mass of a baseball, and you could absolutely play catch with it. However, there are a couple of issues. Like, you could pick it up if you could hold it, but the problem is that you can't hold it, that it would be microscopic, and any of your atoms that got too close to this baseball mass black hole would start to absorb some of your atoms. So you wouldn't be able to hold it. Also, it would evaporate. So, you know, anything smaller than a small asteroid, like a house-sized asteroid, will evaporate within about a day. So there is no way to have it remain stable, and there's no way to touch it, pick it up, except using gravity. Aturuxo. How much confidence is there in the distance ladder? Could the Hubble tension be due to some mistake in one of the steps? For example, standard candles always give me a funny feeling. The distance ladder is this thing that astronomers have done to build up a way of measuring distance in the universe. And the problem is that the best, most accurate versions of the distance ladder start to fall off over time. So the gold standard in the distance ladder is parallax. And this is the method that the Gaia mission used to measure distance in the universe. And what you do is that you sort of imagine, and I always use the example is like, imagine, hold your thumb out at arm's length. Hope everybody's watching this is doing this right now. And then just open and close your alternating eyes. And you'll notice your thumb jumping back and forth. Now, your thumb isn't jumping back and forth. It's your perspective that's jumping back and forth. And so then what the Gaia mission did, and what astrometry and the parallax method does in general, is that you're on one side of the sun's orbit with the Earth, and you take an image of the night sky. And then you're on the other side of the sun's orbit, and then you take an image of the night sky. And you're looking for foreground objects to jump back and forth over the course of an orbit. And then you can use geometry to calculate the distance that the Earth is on the two sides of the sun. And then you can measure the angle that you get to that star in the different configurations. And that allows you to create great big triangles that allow you to measure the distance to that star. And it's incredibly accurate. And the Gaia mission was designed with this in mind, and it measured the positions of like 2 billion stars by the time this is all going to be done at a fairly large distance. It can measure them out to like the distance to the center of the Milky Way. And that's the first rung of the distance ladder. And it is, like I said, incredibly accurate. The Gaia is the most accurate thing that's ever been developed for this, and it's been able to then reinforce the rest of the distance ladder. The next one is the Cepheid variables. And the Cepheid variables are also very well understood. You have this giant star that's pulsating at this rate that is based on the amount of total luminosity that's giving off. You can double check because there are Cepheid variables that are close enough that you can use astrometry. You can use the parallax method to know where they are. And we know that these Cepheid variables highly accurately tell you the period that you see of it brightening and dimming tells you the amount, how bright it's going to be. And then you measure the brightness, and that allows you to know the distance. And so the Cepheid variables takes you out into other galaxies. And it is, again, very accurate. And this is what astronomers have used to measure the expansion rate of the universe. This was where Hubble made his original calculations, and people have just gone and done better versions of those with James Webb and the Hubble Space Telescope. After that, the distance ladder starts to become less accurate for a while, harder to make sure and absolutely pin down. There can be more confounding factors. The classic example of this is the Type 1a supernova. That, we know that when a Type 1a supernova goes off, it's detonating with a very specific amount of material. They are a certain level of intrinsic brightness. And so when you measure one of these supernova going off, you know what its true brightness should be. You measure its apparent brightness, and then that tells you the distance. And then you double check this calculation with Cepheid variables, and you get this overlap. But you can't do the parallax method to get to the type 1a supernova. And so you're having to use, the distance ladder is laddering you out to these distances. And then and that's very accurate. And there's a recent study done by Adam Rees and the rest of the Nobel Prize winning team that helped measure the expansion rate of the universe and helped discover dark energy originally. And he has gone back and used James Webb and double checked the Cepheid variables and double checked the type 1a supernova and made sure that even in this next generation of instruments, you're getting those same answers. And then beyond that, the distance ladder starts to become a lot more wobbly. So you've got the brightness of quasars, you've got gamma ray bursts potentially, and other things that are bright. The one that's really interesting is gravitational waves, that when you have, say, two black holes collide with each other, then you can actually find out their distance just from that collision. And maybe that's a separate video. At some point we'll talk about this, but that you can then know with incredible certainty the distance that occurred. And it's independent. Like you don't need to know its apparent brightness. You can just calculate the distance. But it's not as precise as these other methods yet. And so in a perfect world, if we knew some of the parameters of these mergers of black holes, that would actually be one of the best tools for the distance ladder. They're considered a cosmic siren, that they would tell us distances. We would know exactly where these mergers happen. And so if it happened in a galaxy, then we would know how far away that galaxy is. And then you kind of come back to the accuracy. The final method of the distance ladder is the cosmic microwave background radiation. And this has been measured with incredible precision. So, the distance ladder is very well understood. It is double checked. Of course, like you, the astronomers are concerned that they can't rely on it. And so they double check it and double check it and double check it and do a lot of work. And some of the best papers have come where astronomers have just done the most comprehensive reevaluation of the distance ladder to check every little piece of it and make sure that it still holds, because so much of modern astronomy is built up on this distance ladder. And people are concerned about it, and yet people are very confident that all of the bits and pieces of it still are very accurate. It's time to shout out our new patrons at the $5 level and above: Raid Panda, Daniel, Mark Mueller, Stephen Challam, Jose Garcia, Tyrantula, Pal Bendixson, Karel Vondrak, RGD, and Dwight Pridham. Join our community at patreon.com/universe today. Pelican 666, what is the point of continuing the Voyager mission? Isn't it a waste of the Deep Space Network? The Voyager spacecraft are the only spacecraft that humanity is contacting that are in interstellar space, that they are no longer in the region that's dominated by the solar wind that's coming from the sun. They are in the region that is dominated by the interstellar medium. This is the combined solar winds of all of the stars in the region. And this is a unique environment, a place that we've never been to. And so the people working with the Voyagers have been shutting off their instruments as they run out of power, but they're leaving the ones that are useful for being able to explore the interstellar medium. And this is incredible, right? Like, this is what permeates all of the galaxy outside of the local bubbles around each one of the stars. So no, they're doing still incredibly valuable science. We measured as they crossed the helioshock into interstellar space, and how with increased solar activity, the helioshock engulfed them again and then came back again. So no, the Voyagers are doing such important science. It'll be like right to the bitter end. They'll be continuing to pull science off of those spacecraft, and it's incredibly valuable to use them with the Deep Space Network. And in fact, the work that they're doing is so important that now NASA and others are figuring out how to do an interstellar mission. Now, not a star that will not a mission that will go to another star system, but a mission that will go out into interstellar space, the same place that the Voyagers are, and also continue to gather additional information out there using the baseline data that the Voyagers gathered for us. Cooper Levesque, wouldn't life have to be found in an extrasolar system to suggest that life is universally abundant, as opposed to finding life on Mars or Europa? Yes. If we find life on Mars, or if we find life on Europa, the question that we have to ask is, are we related? Did life make the journey through panspermia, where you could have asteroids crashing into Mars, blowing debris into space? There could be microbes on that debris. It could survive the journey through space, crash onto Europa, and then life could find a way on Europa, or vice versa, or some mix of this, all of the above. And so when we actually do find life on Mars, or if we find life on Mars, then we're going to have to search for a common ancestor. Are we related to the life on Mars? And if we do have a common ancestor, then it means that some version of panspermia happened in the past. And if we find life on some other solar system, then we can imagine an easy way that we share a common ancestor, but not necessarily. People have proposed that life could make its way from solar system to solar system. You can imagine one scenario where, say, a giant comet passes just through the upper atmosphere of the Earth. It doesn't actually crash into the Earth and scoops up a bunch of life and then moves on some trajectory, leaving the solar system. And it would be carrying life to some other solar system. Or you can imagine there's, all of the debris that has been kicked out of Earth or from Mars or whatever from these asteroid impacts. It's just, trailing behind the solar system and finds its way to other star systems. And if this is happening in every single star system in the entire galaxy, then material is being swapped back and forth from star system to star system. And so it could very well be, in the far, far future, we send a spacecraft to another star system, we land, we find life there, we find that it also has DNA, and we determine that there is a common ancestor, that we and that life share a common ancestor. And this message just keeps coming up over and over and over again, because maybe there's only one origin of life in the galaxy, and yet everything is related to that. So we have so many questions and no answers that we have to just keep looking. Edward, if we found a microbe without any DNA, is it even alive? I mean, if it's doing the things that life does, then it would still be alive. Life, it's funny. You ask people, what is their definition of life? And you'll get as many explanations as there are different kinds of scientists. Some consider that life has to have a membrane and extract resources and energy from its environment and poop. Other people have a much sort of less strict version of what life would be. It's kind of like you can't describe it, but you know what it is when you see it. And I think if we saw some kind of microbe that was interacting with its environment and was replicating, and even if it didn't use DNA, it used some other system, it would still be doing the same functions as DNA does with Earth life. So yeah, it would be alive. A lot of people say, like, why are we searching for life as we know it when we should also be searching for life as we don't know it? And of course, scientists are searching for life as we don't know it, and have come up with, non-specific ways of searching for life. Like, you count the number of chemical bonds in a sample, and that the more complex the molecules are in your sample, the higher likelihood that life was responsible for its creation. And it's agnostic. You don't have to know what kind of life produced it. If you're just seeing a lot of really long chain molecules in your sample, that's more likely that life formed it. And it doesn't matter whether it uses DNA, RNA, carbon, anything. Cooper Levesque, do you ever get bored covering a topic or find it redundant? Yes, I have no interest in covering routine rocket launches. A SpaceX Falcon 9 launched a cargo of Starlinks into this orbit. I don't care. We don't report it on Universe Today. I don't talk about it on Space Bites. I just don't care. And there's other channels that definitely do. I mean, you can go watch Market's House. You can watch Scott Manley, Just Have a Think, Alien Space, Tim Dodd. I mean, there's a lot of people that are covering NASA spaceflight, Dust Padre. So lots of people are covering every single minor rocket launch that's happening I don't. So I would say that is the thing. Maybe it's my biggest blind spot. You know, a lot of the times when I'm reporting on spaceflight, I'm looking for things that are new, things that have changed, things that are new capabilities, or rockets that are launching, payloads that are really important to me. I don't really care that much that a rocket has launched at this point. And there's such good coverage from all those other people that I just mentioned, right? Like, what's that? 8 channels who are covering every single, and there's like even smaller channels. They're covering every single aspect of spaceflight. So I don't need to. I'm more interested, you know, I cover the stuff that nobody else is covering. You know, Anton Petrov is like the closest. You know, there's overlap on stuff that he covers and stuff that I cover. Sometimes stuff that Sabine Hosseviller covers, I've covered. But mostly I cover stuff that nobody else is talking about. And I feel really happy about that. And mostly I'm just following my own curiosity. So yeah, but rockets. And like, you know, a lot of the times Anton, like when we prepare the list of stuff for Space Bites, Anton is much more into rockets than I am. And so he'll throw a bunch of rocket stories into the episodes. But I personally don't spend a lot of time thinking about rockets. Did you know you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. This week's bonus question is all about whether it's worth filming a movie in space, and I'll put a link in the show notes. All right, those are all the questions that we had this week. Thank everyone who put your questions into the YouTube comments, as well as everybody who joined us for the live show. We record the show live every Monday at 5 p.m. somewhere in the world, and it's 2 hours long. It's a great back and forth. I get to dozens and dozens of questions. We can only show a fraction of them here in the final edited version. So check that out. I should have an event for the next live show somewhere here on the channel. All right, I'm going to talk a bit about why we put our content over on Patreon. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bray Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gildenet, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Modsel, Paul Roebuck, Ren Kaidu, Robeck, Sean Sargent, Stephen Fallon Munley, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So you've probably noticed that I mentioned that you can watch longer versions of our content over on Patreon. And, you know, I see complaints in the YouTube comments about the fact that we do this. Why don't we just post our content here? And I'll give you some really good examples. And so the first example of this is that YouTube uses an algorithm to show you our content. And so if YouTube decides that our content is not the kind of content that it wants, that it would prefer to show you, say, AI slop, it will gladly do that. If it wants to show you shorts, if it wants to show you live streams, if it wants to show you stuff that it thinks you're going to like better, then that's what it'll do. And it doesn't matter whether you have been enjoying the content from our channel. The algorithm is what decides. And I think it's a terrible way to curate the kind of information that you're watching. You don't want to lean back and just let a machine decide what you watch. You want to curate and choose the channels that you follow and then be able to watch the content from those channels. And so we release everything completely for free over on Patreon. So you don't have to subscribe. You don't have to sign up. You don't even have to have a Patreon account. We just put those links over there. It's the full content. And then to reward you, to train you, we make them longer. And so we put in one additional question or one additional news story or whatever. And so in our perfect world, what you're going to do is you're going to go over to Patreon, you're going to set up a free account on Patreon, and then you're going to follow our channel. And then you will get notifications every time we release a new video, not based on an algorithm. And if you don't want to do that, that's totally fine. Like if you just want to stay on the YouTube main page and just keep clicking refresh, and then you see a bunch of new videos and you pick one and you watch it, that's fine. But you're going to have this unsettling feeling that there were channels that you used to like and they just slipped over the cosmological horizon and you just never stopped seeing them again. And it's not because they weren't good, and it's not because you weren't interested in them. It's because the YouTube algorithm changed and didn't keep your interests up to date with it. And then at the same time, I want you to do this experiment. Go to the YouTube search box, type in, say, James Webb Space Telescope, but then filter the search for the last week, or maybe the last month, or even the last year, and see what the search results give you, and look at the kinds of videos that you're looking at, and then judge if that's what you want the algorithm to be feeding and to be pushing into your information diet, because that's what's happening. All right, so if you don't want to follow us over there, no problem. But if you do, we'd be glad to have you. And again, it's not about money. It's about maintaining a direct connection with the audience, the people who want real space journalism. All right, we'll see you next time.